now be joined by Ioana Cozmuta. She's a doctor. She's the co-founder and CEO of G-Space, and she's going to talk about space manufacturing here, the next generation of materials. So welcome. Good morning. We look forward to your presentation, and let me hand it off to you. Thank you.
Yes, hi, good morning. Can you hear me?
Yes, yes.
Okay, just checking that everything is working there, and you can see my screen too?
Screen looks good too, yep.
Okay, perfect. Thank you so much for the opportunity to be here. I indeed will talk about space manufacturing, which interestingly enough, when I was growing up, I never thought I was going to work in this area or even have the opportunity to be inspired by such a fascinating topic. I probably would have thought about it as being to the realm of, or belonging to the realm of science fiction, and very possibly people today, many people today think of it as being something of, the future, 20, 30 years in the future. And yet here we are manufacturing things in space today, which is the narrative that I hope to walk with you together today. So where do I come from in this field? I worked at NASA for 15 years, and one of the areas that I was recruited in back in 2012, so it's almost 10 years, was to take a fresh look at the International Space Station commercialization, what came out of it, what are still barriers that need to be removed. So in reviewing the entire database of material and life science that pretty much humanity has performed in microgravity and in space, of course, I asked the question of how is that relevant to, in particular, to industries terrestrially. So that's the core of my expertise here, or my credits, if I were to put it this way. I won't go too much over why now, because timing is extremely important, and Peter Platzer already talked about how vibrant this new space, what we refer to as the new space industry is, and in particular comparing investments in the past. So the timeline here, the tipping point is 2010. The investment in the past were primarily government, and the government was developing technologies for its own use, versus what we see right now is a very wealthy and prosperous ecosystem forming around these government investments, and actually becoming independent of these government investments, balancing out the forces where the paradigm shift is that the government just becomes a customer of many. And so what we see happening in the new space industry, what has turned from an emerging market 10 years ago to a very trustable market these days, and it really stemmed from the development of these small satellites, is Earth observation, the diversification of launches, and providing satellite connectivity from space, right? Internet from space, Earth observation, and providing frequent access to space. We see that private investments flowing into space have increased in the order of billions, and there are over 500 VC funds investing in space. So what did this result to, right? This diversification and growth has resulted in lowering barriers, and lowering barriers means having more frequent access to space, more frequent and reliable access to space, decreasing the pound per kilogram to LEO, GEO, MEO. So increased access, increased reduced costs, unprecedented diversification, but also increased government spending. And what we see is that the number of countries investing in space in the world is at a very steady increase. So it is more than double in the 2020s compared to the 2010s, which means that a lot of countries see this as a very important area of development. So this is absolutely a hot $1 trillion industry, and I don't need to restate the obvious here. There's investment bankers and entrepreneurs and major industry players who are really not only stating the obvious, but predicting that the growing space economy will more than triple in the next decade. Within this amazing industry, in-space manufacturing has a central place. So we're really talking here about the second wave of new space companies. And back in November 2020, Research and Markets has published a report talking about the 3 new trends in one report: the in-space servicing, in-space transportation, and in-space manufacturing. Now, it is really hard to put a size for this market because this market is now emerging the same way Earth observation market or satellite from internet from space was emerging in the 2010s. But we're really talking here about an exponential growth and a significant CAGR for the next decade. So in from these 3 areas, I will in particular focus about the in-space manufacturing. And so there are 2 lines evolving here: products that we manufacture in space for Earth. So the left side, space for Earth, for terrestrial use on terrestrial markets, and products that are manufactured in space for space use. So space for Earth and space for space. And in particular, the in-space manufacturing, I will be talking about materials manufactured in space, advanced materials manufactured in space. But there's everything stems from this microgravity R&D market that has been around for more than a decade right now, which is about $10 billion. What we see today being manufactured in space, and there are several companies doing that, is fiber optics. However, there's opportunities growing for markets to grow into semiconductor, batteries, biotech, and others. And the numbers that I'm putting here for these markets is assuming that a certain percentage of the terrestrial markets will be captured by these products manufactured in space, given that these products that will be manufactured in space will hit very clear performance characteristics, superior and unique to what we can manufacture terrestrially. So let's talk a little bit about this space for Earth. There's many promising areas. In fact, part of my work in the past was to take a look at what has happened during the efforts in commercializing products from space during the space shuttle era. And so the reason that really didn't pick up on a commercial basis was really the parameters, the barriers that we were talking before. We didn't have frequent access to space, and the cost was prohibitive per kilogram. But this binning of these products, right? What I try to do here is I try to put them to align with different industry verticals. And in fact, if you really want to successfully commercialize a product that's manufactured in space, you need to find an infusion point for a terrestrial industry roadmap of that product. So we're talking here not only about new materials, but computer and communications. Back at NASA, when I was at NASA, I actually helped start this spaceborne computer. Biotech. Sorry? Do you have a question?
No.
Okay.
It might have just been background noise. Sorry.
Oh, no problem. Okay. Biotech, medical devices, as well as consumer products. So how do we think about these products. Why should we manufacture these products in space? And again, I will talk primarily about materials beyond, their the factor of being sensational and being manufactured in space. So gravity actually has a grip on flames. For example, the space flame on the right is spherical and not elongated like the one on the left. So not only there is less oxygen to burn, but the shape of this is affected by the lack of buoyancy or convection. For protein crystals, the space crystals on the right are larger and have reduced mosaicity, which connects to the amount and the size of defects in that structure. Space materials on the left have homogeneous distribution and again, less defect. But ultimately, the gravity grip has it's really broad and it really covers the fundamentals of the phase diagrams of many materials and also helps upon its removal to expand to new area of stability. So there's what we can do in space because of lack of gravity is no buoyancy, access process with longer timelines, and exploit the idea of homogeneous mixtures. On top of that, the space environment has additional advantages, right? I'm talking here about solar power, ultra high vacuum, no gravity, and ultra low temperatures, all of these for free, because even if we create vacuum terrestrially, it costs us energy. If we create a weightlessness environment terrestrially, first of all, it is at a reduced scale, but it also costs us energy. So we really have, this free power, free vacuum, free weightlessness, and free cooling. The materials manufactured in space are unique in their design and their production, and they will feed the needs of the digital age, such as telecommunication, right? We're talking here fiber optics with predicted 10 to 100 time attenuation, quantum application, quantum dots, 10 to 100 time more homogeneity, DNA electronics, DNA nanocircuits, 10 to 100 time more resolution. But the question that remains is, how do we make sure that we create these superior products that are of relevance to Earth markets? So the holy grail of in-space manufacturing today, when we talk about the space for Earth, right? And we're really talking here about advanced material. We will not go and make their, regular plastic for Earth use. We may create that maybe later on for space use. So the holy grail is to find something that has a high ratio of value to mass, that you can manufacture in high volume, that these materials have a unique performance, they have high energy consumption when manufactured terrestrially, and that you identify these customers who want to pay a premium for that unique performance. So in fact, in-space manufacturing is not a matter of developing yet new hardware and flying hardware up and down into space and putting yet new infrastructure. It really is a multidimensional optimization process that can be solved through AI, data science, and material science. And this is, in fact, one of the major things that we're doing at G-Space. We developed a platform, an AI platform for gravity-independent materials, where we discover and optimize these materials under terrestrial non-gravity conditions at a small scale, but then we use our AI and machine learning algorithms to scale this design up and to establish what would be the correct manufacturing conditions in space. We would also monitor those in space, and we help reimagine, in fact, in-space manufacturing. And what I mean by the last one is a lot of the hardware that is being used today in the manufacturing of these materials in space is at best a miniaturization of a terrestrial gravity assist process. We're really talking here about inventing or discovering and driving towards in-space manufacturing process that are native to space. So our Atom platform, the advanced terrestrial to optic orbital manufacturing, has 4 modules. One, the Scout module that's focused primarily on microgravity product design, the Compass, Atom Compass product optimization, and then the last 2 modules, Fusion and Radar, really have to do with the product qualification and product manufacturing and monitoring. Because if you think about it, not only, again, you need to determine what material you need to manufacture in space, in what volumes, but you need to make sure that you follow now that, or you monitor the manufacturing process in space to make sure that you hit the performance characteristics of your product, that that environment and the manufacturing envelope really is consistent with the design, with what was designed. And so that will then underlie or create a basis for the qualification and certification of these products so that they can be put they can be delivered and sold on the terrestrial market. So examples here, it's just a sample of the multiple algorithms and techniques that we use as part of G-Space, which is a versatile and of use to multiple industries. Goes from really taking a deep look into materials and material changes as function of different environmental parameters. And of course, at the core, at the central core of all these platform is the extraction of this delta to gravity. And what does that change mean for a product that is needed on a terrestrial market? So you can also consider here that we're merging information about the impact of gravity and monitoring this impact, capturing this impact, optimizing for it, but at the same time creating an exchange, stock exchange for materials between space and Earth. So we consider ourselves that through this platform, not only we will be fully focused on this in-space product design for terrestrial market, but this would enable a 10-time cost reduction in what is being done today. And it will truly and authentically create a connected space enhanced value chain for the manufacturing of materials. So let me talk a little bit about the space for space. Today, the space infrastructure, and there's a multitude of space provider out there, is being built, whatever we have in space, whether it is the James Webb Telescope, whether it is synthetic aperture radars or solar panels, the materials are really developed terrestrially, mature terrestrially, tested terrestrially. The structures then are built terrestrially. They are de-risked and space qualified terrestrially. And we margin them unnecessarily because they have to now go through this envelope of the launch environment. So we're really stuck with thinking from the bottom of the gravity well in many, many different perspectives. So the space for space idea, right, goes into really requires this paradigm shift, right, where instead of creating all these structures and qualifying them and margin them terrestrially, we would send into space at the first step the raw material from, the raw materials will be terrestrial. They will be designed terrestrially, but having space in mind, having in mind the ultimate environment where these materials need to perform. And so then, they actually will be manufactured in space and leverage, like I said, from all those free things that we have available there. To shift in the future into once, setting in space this infrastructure between the Earth Moon system, we will be able then to connect with the effort of extracting raw materials or accessing raw materials on the moon, on asteroids and other planetary bodies, so that we augment this source of raw materials that originally will be terrestrial with other sources. So this is where we see. I hope I gave you a good intro and a good overview. I know the time was short, I very much thank you for your attentions, and please connect with us to build futures for space.
Thank you, Dr. Cozmuta. Fabulous. It's amazing. You take all of that technology and science, but from a business audience standpoint, when you start talking about the compound growth rates that you mentioned, the cost savings, it really does bring it home, which was very fascinating. Whether it's space for space or space for Earth. Who knew gravity could be that helpful, right? How about
yeah, exactly.
How about that? Well, listen, your speaker information is in the tab. So if anybody wants to connect with you, they're welcome to.
Sure, absolutely. Thank you.
Thank you for your expertise. Thanks for all you're doing, and thanks for being part of our conference here this week. Much success.
Absolutely,
Right.
my pleasure being here. Thank you.
All right.